It follows from Helmholtz's theorem, see Helmholtz decomposition. The general metric perturbation has 10 degrees of freedom. The vector and tensor fields each have two independent components, so this decomposition encodes all 10 degrees of freedom in the general metric perturbation. Using gauge invariance 4 of these components, two scalars and a vector field, may be set to 0. The tensor field is traceless under the spatial part of the background metric, I.E. The vector is written where and is the covariant derivative defined with respect to the spatial metric. The notation is used because in Fourier space, these equations indicate that the vector points parallel and perpendicular to the direction of the wave vector, respectively. Thus can be written as a combination of a scalar and a divergenceless, two-component vector. Finally, an analogous decomposition can be performed on the traceless tensor field. It can be written where is a scalar, the combination of derivatives is set by the condition that be traceless, and where is a divergenceless spatial vector. This leaves only two independent components of, corresponding to the two polarizations of gravitational waves. Since the graviton is massless, the two polarizations are orthogonal to the direction of propagation, just like the photon. The advantage of this formulation is that the scalar, vector and tensor evolution equations are decoupled. In representation theory, this corresponds to decomposing perturbations under the group of spatial rotations. Two scalar components and one vector component can further be eliminated by gauge transformations. However, the vector components are generally ignored, as there are few known physical processes in which they can be generated. The tensor is gauge invariant, it does not change under infinitesimal coordinate transformations.